You can use the normal approximation with the binomial distribution as long as your number of trials is large, because then they're going to kind of become similar to each other. So let's just talk first about what the binomial distribution is. Remember, it has a fixed number of trials. Each outcome is independent, and the big thing here is there will only be two outcomes. And the probability of success must remain the same for each trial. So these are the characteristics of a binomial distribution. Now, to use a normal approximation for a binomial distribution, I know lots of big type words here, but basically, remember binomial distribution, you have two outcomes. Either this is going to happen or this is going to happen. And our normal approximation is when we're saying this bell-shaped curve and our probability under this curve. How can we match up these two things? So, think back to a binomial distribution. N, our number of trials, P, our probability of success, and then we also had a Q, which is our probability of failure. When P is approximately equal to 0.5, and as N increases, the shape of the binomial distribution becomes similar to that of the normal distribution. So again, when P is approximately 0.5 and N increases, the shape of the binomial distribution becomes similar to that of the normal distribution. The larger N is and the closer P is to 0.5, the more similar the shape of the binomial distribution is to that of the normal distribution, that bell-shaped normal curve. So, here's what we want to say. Normal approximation should only be used when N times P and N times Q are both greater than 5. Or I should say greater than or equal to 5. So, the gist of all this and everything here, if we want to use our normal approximation, meaning our normal approximation table and all that information with a binomial distribution, as long as our number of trials times the probability of success and the number of trials times the probability of failure are both greater than or equal to 5, then we can use it. Here's kind of what happens. If you look right here, and I know this is kind of small, but it says N is equal to 10 and P equals 0.3. If we were to multiply those together, we basically just get 3. That's not greater than or equal to 5. And that's kind of represented, remember our binomial distribution, if we were to graph it, is represented by these lines. It's discrete. And you can see that it doesn't quite match up. No, it's not far off, but it doesn't quite match up. But if you look, if we did a binomial distribution for number of trials 10, again, usually you want more trials than just 10, but just for this example, and our probability equal to 0.5, if you multiply those together, you get 5. Look how much better that matches up with our normal distribution curve. So basically what it boils down to, we want our NP, or N times P, to be greater than or equal to 5, and NQ, again that's number of failures, to be greater than or equal to 5. If this happens, then we can just use the normal distribution model we've been working with. That kind of leads us to a correction for continuity. It's a correction employed when a continuous distribution is used to approximate a discrete distribution. Binomial, discrete. Normal, continuous. So discrete, there are these lines here, and the whole area underneath it, that's continuous. So we have this correction we use, and that comes into this chart right here. Basically, if we want to define the probability of x, our value there, equal to 8, we've got to make a little adjustment to it because this is a binomial distribution and we're using a normal approximation. So if you look right here, it says when it's exactly equal, we're trying to find the probability of something equaling 8. We're going to adjust it 5 down and 5 up. Think way back to months ago when we were doing kind of some graphing with boundaries and we were adjusting our boundaries so there'd be no overlap. That same idea. So we would just take this right here and we're going to take our value and subtract 0.5, which would be 7.5 or 7.5. And then we're going to add 0.5, which would be 8.5. And then when we have this kind of correction here, this adjustment, we're going to be able to use our normal approximation to find the probability. Same thing if I had something like probability that our x is less than or equal to 7. We'll look down here, x is less than or equal to a, we want to use this one in here. So we're going to take our probability, I think I was looking at this one here. X is going to be less than, notice we're dropping there or greater to, because we're making an adjustment, to 7.5. This is hard to memorize right here, so just have it handy. Refer to it. And then don't forget too, we're going back to using our mean here is going to be n times p. Our standard deviation is the square root of n times p times q. And again, we're following these rules that they have to be greater than or equal to 5. One more thing going on along with this. Here's our procedures. These are the steps we're going to follow. Just do step 1, 2, 3, 4, 5, 6, and you're going to be able to find the solution. I'll read through them quickly. An example will make more sense. First of all, we're going to check to see whether normal approximation can be used. What do we mean by that? Right here. N times p and n times q, are they both greater than or equal to 5? Find the mean and standard deviation. Again, use this. Our mean is n times p, our standard deviation is that square root of NPQ. Rewrite the problem in probability notation using x. That's what I was doing right here. Rewrite the problem using the continuity correction factor. That's this part right here. So none of this is too overly hard yet. Find the corresponding z values. Again, we're going to be using then z is equal to our value minus our mean over our standard deviation, and then use our table to find the solution. So looking at an example, magazine reported that 6% of American drivers read the newspaper while driving. If 300 drivers are selected at random, find the probability that exactly 25 say they read the newspaper while driving. Go through your steps. Step 1. Our number, remember N stands for number of trials. We're talking about 300 drivers. Our probability of success, not necessarily that this is successful, but what we're looking for is people who read while driving, read the newspaper. And so that's going to be 6% or 0.06. That means our Q is going to be 1 minus that, so 0.94. And then we just multiply them together. N times P is 300 times 0.06, which is 18. N times Q is 300 times 0.94, which is 282. Both of these numbers are greater than 5. Done. We can continue, move on to step 2. Step 2, find the mean and the standard deviation. Well, our mean is just n times p. So we actually already did that right here. 18. Our standard deviation is the square root of multiplying all these together. So 300 times 0.06 times 0.94. Multiply those and take the square root, which works out to approximately 4.11. Step 3, write the problem in probability notation. Well, we're interested in exactly 25, so I want the probability they're exactly 25. Told you these steps don't take too much, so don't be intimidated by the fact that there's 6 of them. Step 4, rewrite the problem using the correction factor. Well, we're dealing with 25, equal exactly to 25. So let's go here. You look right here, this is the one we want to use. A half, or 0.5 less and 0.5 greater than our 25. So half a point less than 25 would be 24.5 is less than x, which is less than, add 0.5 onto it, 24.5. Almost there. Now step 5 is when we start getting into our z factor, or z values. Find the corresponding z values. Let's start by sketching a rough picture here. Remember, normal approximation. Our mean, the middle number here, is 18, and I'm interested in 24.5 to 25.5. Okay, so I'm interested in all of this right here. So, using our z-score, let's do z1 and z2, and I'm going to take 25.5 as being my z1. So 25.5 minus my mean of 18 over my standard deviation of 4.11 works out to approximately 1.82. And then let's do it again. Just call it my second z-value here. Using our same formula, but this time I'm going to use 24.5 minus 18 over 4.11, and that works out to approximately 1.58. Found our z-values. Almost there. Step 6, find the solution. Well, go back to using your chart, your normal approximation chart, and find these two numbers on there. Our z1 value, 1.82, corresponds to 0.9656. Our second z value of 1.58 corresponds to 0.9429. Again, if you need any help reading that table, make sure you ask, I'll help you with it. We want the difference between these two, so we just subtract them. And doing that, we get 0.0227, or 2.27%. So, binomial distribution, either read the newspaper or you don't, but because it's a high enough number of trials that we can use the normal approximation on it, if we want to find the probability out of 300 drivers selected at random that exactly 25 say they read the newspaper while driving, that's only about a 2.27% chance. Not very high, but that seems kind of reasonable. Again, what we're doing in this lesson is we're taking our binomial distribution, we're aligning it with or using our normal approximation to applying it to our binomial distribution, and we'll be able to figure out our percentages based on our standard normal curve right here.